This is lecture on Module 2, lecture number 8. We will be continuing our discussion of research design and data management, and we are focusing still on test statistics. In this lecture we'll talk about critical values, the t-tests, and the f-tests. First, remind ourselves of some of the basic properties of normal distributions. Here we see the frequency curve for a sample population, or actually population data. We notice that the mean is mu, so that's population data. So it's the frequency curve for the general normal distribution. Mu and sigma are the population mean and standard deviation. The p sub x, the px is the probability density, and x is the variate. So we're reminding ourselves that mu is the point of central tendency for a normal distribution, and we have plus or minus 1 standard deviation, 2 standard deviations, and 3 standard deviations, and this is the focus of our attention. We'll start first by evaluating whether any value of x might have come from this population. If it exceeds the plus or minus 2 standard deviations, it would be considered that it would not belong to this population. So we want to build on that idea, because when we're comparing samples, we focus on that 0.05, which is significance, which is the plus or minus 2 standard deviations away from the mean. And this will become clearer when we proceed through this in a stepwise fashion. First, to talk about whether any one value that you might get, like in manufacturing, if you're measuring the tolerance on some piece of product, does that fall within the accepted standard for that population? If not, the part would be discarded or excluded from going out to the market. We don't use this very much, but I like to use it as a stepping stone to proceed to the second level of comparing the means of two populations using the t-test. So by going through this stepwise, we gather a stronger appreciation for the test statistics that we end up using most frequently in our studies, which typically would be applied to comparing at least 2 normal distributions. And here we see 2 distributions with their means, so 2 normal distribution frequency curves. The first one, mu is 2, and the standard deviation is 2/3, or 0.67 basically, and population 2 is a mu of 5 with 1.5 as the sigma, the standard deviation. So we if this was the actual population, this was a sample, the differences between the x bar and the mu would be bias, and so it would not be a very precise measurement, and it would not be very, this one would not be very accurate because of the high dispersion around the mean, the high standard deviation. So we recall that from our prior lectures. The t statistic that we'll be talking about is if these were 2 sample populations, then would these means be statistically significantly different from each other? And the area of concern here, of course, is this overlap between the 2 sample populations. Just what kind of a risk would this overlap in our sample points generate toward leading us to conclude statistically that these 2 means are not statistically significantly different. And looking at the low level of precision on this sample, the dispersion around the mean, and this amount of overlap, we would predict that these 2 could not be statistically distinguished as 2 distinct populations. So this is what we're heading toward as we proceed toward adding a 3rd or a 4th or more complex types of sample measurements and the statistical analyses appropriate for those. So we start then with reminding ourselves the simple quantitative presentation of data for a normal population is the mean, variance, standard deviation, and the standard error of the mean. We'll discuss each of these from the perspective of population first, looking at the formula, and then the observed, the one that we typically would use to perform our statistical calculations. Calculation of the mean, we see mu here, so we know this is on the population. So the frequency of x1 plus the frequency of x2, and so on and so forth out to the n, the total sample, the total population size divided by the frequency of 1, 2, on out to n produces the mean for the population. This, we see the x bar, so we know that that is the sample population, the sample mean, that we think is representing the population, and that is calculated, of course, as we know, by taking the sum of the sample points, x sub 1, 2, out through n, the sample size, divided by the total sample size. So the sum of x over n. This is the observed for samples. Variance is the next, and we see the capital V, so uppercase V, so this is for the population, and it is the frequency of x1 minus mu, the population mean, squared. So on through the total population size, f sub n, x sub n minus mu squared, and of course over the sum of the frequency of these, and this basically is the mean squared difference, as we're seeing here, the sum of the mean squared difference for the population, which when divided by some representation of the population size or sample size, in this case you should recognize this as the degrees of freedom that we'll describe in a moment, produces an estimate, in this case, of the variance. So lowercase s squared is the sample or observed variance, and there's two ways of looking at this formula. It's each sample point observation, x sub 1 out through x sub n, with the mean, the sample mean subtracted from it, so the difference between each sample point and the mean squared, taking the sum of those divided by the sample size minus n. Another way of doing this is adding up the square of each of the observation data points and subtracting n times the mean squared over, again, the n minus 1. Either of these formula approaches calculates the variance for the sample, the observed variance. And of course the standard deviation for the population or for the sample, the observed, is the square root of the variance. Population formula shown here, sigma squared equals variance, so you take the square root of variance and you get the standard deviation for the population. S squared is the variance of the sample, or the observed. You take the square root of that and you have the standard deviation for your sample. Another very important and commonly used estimate of dispersion of data around the measure of central tendency mean, in this case, or mu for the population, is the standard error of the mean. And we'll take a bit of time to describe this because you do see it used so commonly. For the sample, for the population, it is the sample error, which is the this mean sum. This sum of the mean squared differences. We'll explain that a little more in a moment if I can keep pronouncing all of these statistical terms. So the sample error equals, the standard error of the mean. I'm getting ahead of myself and confusing it. I apologize for that. So this is SEM, standard error of the mean, as we typically see it. SE sub x bar as standard error of the mean is sigma over the square root of the population size. For observed, sigma is replaced by the the standard deviation over the square root of the population size minus 1 to produce the standard error of the mean for the observed. So the standard error of the mean is an important result, often expressed in a slightly different manner. Since x bar is used as an estimate of mu, then the difference x bar minus mu can be regarded as the error in using x bar. We're recognizing this as bias. Now, by definition of variance, and since the error of the mean equals mu, should anyway, the variance of the mean should be equal to the error in the difference between the sample mean and the population mean squared, which equals sigma squared, the variance, over n. So the expected value of this error squared is thus sigma squared over n, as we noted, and hence the standard root mean square value of the error, the standard error of the mean, sigma over the square root of n, which is often expressed thus: the standard error of the mean of a sample is the standard deviation over the square root of n. Therefore, the standard error of the mean is the square root of variance of a function of x sub 1 through x sub n, a range of data values, is called the standard error. The standard error gives some idea of the spread of the estimates of the actual population data points from 1 to n. Therefore, the formula, as we said, for your sample to crunch all this down into something useful is the standard deviation over the square root of n equals the standard error of the mean. That would be the formula that you would use in a software package or in a spreadsheet if you're going to enter that formula yourself. So in other words, the mean of each sample varies slightly from the mean of the general population. There's always a bit of bias from which the sample was drawn. So x bar and the mean, sample mean, and sigma squared, the sample variance, are unbiased estimates of mu and sigma squared, the population mean and the population variance. So this is what we are saying. The smaller the standard error of the mean, the less biased the sample is considered to be in representing the true population. So if the standard error bars on a graph are very tall, then you question how much bias there might be in the sample. So in other words, it's an indication of the accuracy. As you recall, the bias was shown here, and the precision is represented by the distribution around the central tendency. I may have confused that a bit earlier in this presentation. Hopefully you were sharp enough to catch me. The accuracy is precision and bias, as you recall. So the standard error of the mean is representing not only the dispersion, but taking into account the view of a potential bias. So the applications of normal sample theory significance tests to test whether a single observation X could come from a normal population with a given mu and sigma. It would be a two-tailed test. So from these discussions will emerge definitions of two-tailed test versus one-tailed test, paired versus unpaired experimental designs. What we will gain an appreciation for in this discussion of testing whether a single observation could come from a normal population with a given mean and standard deviation is an appreciation for the outlier function that is used to determine if a sample point data point in your sample can be excluded. It has to, the formula for that outlier is that the one data point has to fall greater than plus or minus 2 standard deviations from the mean, and we'll see that that puts you at a 5% likelihood where we would exclude this sample point from being in this normal population. So let's go on to see if that becomes clearer as we discuss things. So the test function for this is the C value, the C test statistic, and it is the absolute value of the single observation minus the population mean divided by the population standard deviation. So the greater the difference between x and mu compared to the standard deviation, the less likely it is that x is an individual from the given population. So the farther that this value is away from the mean, if you can picture our normal curve with the mean, the farther you get away from that, the less likely that data point is in this population, or for an outlier estimate on your sample population, the less likely it is a value that should be included in your sample. Continuing again, this is a two-tailed test, and we'll talk about that more as we proceed, but basically a two-tailed test is used when you don't know the direction of the difference. Is it greater than or less than? So if you can't answer that question as part of your hypothesis from our perspective in science, then you have to use a two-tailed test, and it is more difficult to establish significant differences using a two-tailed test. So that'll come through as we proceed to discuss the difference between two-tailed and one-tailed tests. So the critical values of C are 1.96 because only 5% of the individuals in a normal population have variate values differing from mu by 1.96 sigma or more. In other words, plus or minus 2 standard deviations from the mean, and you're outside the 5%, you're outside into the 5% fringe of the sample or population data points, and you probably don't belong in that sample set for the outlier estimate to exclude data points, outlying data points, or in the discussion here, whether a single observation X could come from a normal population. We would make a mistake on 5% of the occasions when X really did come from that population. So if C is greater than 1.96, the difference between X and mu is significant at the 5% probability level, and you would conclude that X is not in the population. If C is greater than 3.29, the difference between X and mu is significant at the 1.1% probability level, and it definitely would not be from your sample population, from the population with the given mu and sigma in this case. So it would be excluded. It would be significantly different from the population under consideration here, and would be excluded. So we remind ourselves again of the normal distribution, again for a population. Mu plus and minus 1 standard deviation includes how many data points? Out to plus or minus 2 standard deviations, what percentage of the population or sample data points, if we're considering this, extending this to think of it as a sample population of data points. And what about mu plus or minus 3, as we saw in the previous slide? So if a data point exceeds plus or minus 3 standard deviations from the mean, is it really part of that population, or should it be included in the sample data set? And of course this slide is showing us that plus or minus 1 standard deviation away from the mean should include 95% of the sample. 68% of the sample, plus or minus 2 standard deviations from the mean should include 95% of the sample. That's where that 5% comes from. 2.14 plus 0.13, basically the 5%, 2.5% on each side. So that's where that 5% comes from in the previous discussion. And plus or minus 3 standard deviations should be 97%, and plus or minus 4 standard deviations should be 99.9% basically of your sample points. So in other words, the cutoff is at the plus or minus 2 standard deviations, where 5% of your data points really are not useful for considering the actual mean and its variance. So for the outlier calculation, you would calculate the mean and the standard deviation for your sample population, and then look at all of your data points, and any data point that was used to calculate that mean and standard deviation that exceed the plus or minus 2 standard deviations on either end of the mean can be excluded, and it is justified statistically based upon this premise that we're making on the C test statistic, in essence. So in continuing with the applications of the normal sampling theory, if you cannot predict the direction of exceeding, here we see the 1.96, so basically we usually say 2 standard deviations on either side of the population mean in this case, or mu, or sample mean x bar for our samples. If you cannot predict whether it is going to be in this direction or in this direction, greater than or less than, you must run a two-tailed test, which makes it more difficult to establish a significant difference. But if you can predict, in this example we're saying we're predicting that any data point that falls 2 standard deviations away from less than the mu is in the 5% likelihood to be excluded. So you notice that the percentage changes, it doubles when you're doing a one-tailed test. But if you can predict the direction of change, then in other words, you're hypothesizing that in my normal control group, if I treat with something or create a condition and take a sample under the treated condition, that sample mean is going to increase. Then you would use a one-tailed test. If you're going into it where you didn't know if it would cause an increase or decrease, a slightly more open-ended question, then you would have to run a two-tailed test. Most often we probably find ourselves setting up enough information to predict the direction of change, so we would run a one-tailed test, and this would be at the 5% probability level. In other words, you're setting alpha at 0.05 to state that there would be a statistically significant effect. So now let's test whether a single observation is significantly lower or significantly greater, either one or the other, than, separately, than mu, a one-tailed test. So the previous one was a two-tailed test. Now we are with a given mu and sigma testing either that it is significantly lower or significantly greater, so therefore it's a one-tailed test. You wouldn't run these simultaneously. It would be either this or this, because you're predicting beforehand whether it would be greater or lesser than. So the question here is, which of these formula is for the lower or greater than values? So obviously this one, the mu minus x, your single observation, over sigma is less than, because if we are going to get a positive number in this case. If the observation is greater than mu, then the C prime prime test statistic would be used, because we need to end up with a positive value. We saw in the previous formula for the two-tailed test that you got the difference between the observation and the mean, and it was the absolute value. So it was going to be positive anyway. So if C prime is greater than the one-tailed critical value 1.645, X is significantly lower than mu at the 5% probability level, so the C prime, as we had stated. If C prime is less than 1.645 or is negative, X is not significantly lower than mu and at the 5% probability level, and you would say that it is included in that population. If C prime prime is greater than the one-tailed critical value 1.645, X is significantly greater than mu at the 5% probability level, and here we're just using the C prime prime formula, and it is the same statement here. If it is not greater than this value, if it's less than that value, then you have a 5% probability that that observation is included in the population. Note that when a critical value, for example 1.96, is used for C prime, the probability is half that for C, that is 2.5 for C prime as against 5% for the C. So here we see a small representation of the table of the critical values for C prime and C prime prime, where the critical values are shown here and the percentage probability level is shown here, the 5, 2.5, 1, 0.5, 0.1, and 0.05. So these are obviously very significant levels here, and you have a high value that you have to generate the critical value. So in other words, in this case, that individual sample point, data point, has to be tremendously different, greater than or less than the population mean. So to test whether a sample mean differs significantly from mu with sigma known. So now we're beginning to ask ourselves specifically about bias on an observed set of sample data points for which we can calculate a sample mean. We don't run these tests typically, but again, we're going through it to remind ourselves that when we think of the difference between our sample mean and population mean, we're thinking about bias, and we're building on this idea of critical values, test statistics, and eventually we'll talk about the t-test used to compare two sample sets. So in practice, we don't rely on one observation if a sample can be obtained without trouble. So for a sample of size n for a normal population, the mean, x bar, is itself distributed normally with the same mean mu, population mu, but with a standard deviation of sigma over the square root of n. Thus the formula for C and C prime in this case for a two-tailed and a one-tailed test are the two-tailed is the absolute value of the difference between the sample mean and the population mean divided by the quotient of sigma and square root of n. The one-tailed is the C prime. In this case, mu minus x bar would be thinking that this is less than the population mean. Again, over the quotient of sigma and square root of n, sample size. So to test whether a sample mean differs significantly from mu, the critical value for the two-tailed and the one-tailed are shown here. The same critical values as C. If C is greater than 1.96, the difference between sample mean and mu is significant at the 5% level, though not at the 1% level. So we'd have to reach the higher critical value to be at the 1% level. So here what we're saying is we're using this to remind ourselves of bias where the sample mean differs from the population mean. If we did run this kind of a test and got a critical value greater than 1.96, then we would have a significant bias in our sample measurement, and we'd have to go and figure out what's wrong, what are the confounds in there contributing to that bias. This would be, in practice, more likely if you had a manufacturer's preset mu and sigma, and you took a sample of what you were producing, and you had a mean and the sample size, you would want to determine, are you greater than or less than their standard, or are you just asking if you are greater than their, less than their standard. You would use this type of an approach. We very seldom do that in our business, but we do need to appreciate that these types of statistics are run, and it does, as I said, reinforce our idea of bias. So if the observed value C, though below, is not far from the critical value of C at the desired probability level, then more observations should be taken if possible. So this discussion is also going to let us focus on N and the impact of increasing sample size on achieving a critical value. So note that the critical difference, 1.96 sigma over the square root of n, falls off inversely as the square root of n, so that doubling n only lowers it to 1 over the square root of 2, which is 0.707 of its previous value, and taking n 100 times larger only reduces this critical value 1/10 of its former value. So in thinking about increasing our sample size such that we are more likely to achieve a statistically significant difference, we see that several-fold increases in the sample size, sometimes tens of hundred-fold, are necessary to have a really relevant impact on the test statistic ultimately. So sometimes just increasing our sample size by 1 or 2 won't have a very big effect, as you see here. If, however, the critical statistical difference is well below the physical difference, there is no point in increasing n. So there are times when increasing n simply cannot have any effect. So now let's proceed to talk about a test when we want to know the difference between two sample means, getting closer to what we might do more commonly with sigma known. However, we usually don't have a known sigma. We calculate the standard deviation for the sample, so we're progressing ever so slowly. So in this case, the C test statistic formula is shown here, the absolute value of the differences between the two means. We are asking whether they are different from 0, and therefore we have to take into account the quotients of the, in this case, the variance over the sample size, the sum of those, and then the square root, where that can be simplified as shown here. So what we're looking at here, if mu minus mu equals 0, so do the sample means distributed with the population mean, are the sample means distributed with the population mean, or are they outside of the population, as we were saying before? So if C is greater than the critical value of 1.96 or 2.58 or 3.29, the differences between that should be S there, differences between the sample means, no, I'm sorry, it shouldn't be there at all. The difference between sample means is significant at 0.5, the 1%, and the 0.1% probability level. So we're building on our appreciation for the differences between means and how that is related to critical values, and establishing the level of significance for stating that something is statistically significantly different from something else at a level of p less than 0.05, 0.01, or 0.001, and so on and so forth. So to test whether a sample mean differs significantly from a given population mu when the variance is estimated from the sample. So we're seeing slight variations building up to the point where we would have a sample mean and a sample variance, but that's fine. So this estimate of the population variance from the sample would be calculated again as the sum of squares, sum of the mean squares over the degrees of freedom n minus 1. So by replacing sigma by s in the test statistic, which was the x absolute value of x minus mu over sigma, we have the modified test function, the t-test function, of the difference between x bar and mu over the sample standard deviation over the square root of n. So we see that here again. So we use it to use the C critical values for T. Oh well, whatever we're trying. Oh, used to use. So you used to use the C critical values table for this T statistic. I forgot the point I was making on this slide here. But W.S. Gossett wrote under the name of student, was the first to realize that that was incorrect. So now we recognize the source of the name, the student's t-test, and a t-table for it. So later, Fisher worked out the sampling distribution of this statistic, the t-statistic above, which enabled the correct critical values to be calculated. The t-table that we are all somewhat familiar with, the critical values of t. So we see the degrees of freedom. So note that these critical values depend on the quantity of v, lowercase v, called the degrees of freedom, which is in general the same as the denominator in the formula for the variance. So therefore v equals n minus 1. The degrees of freedom equals n minus 1. So if we're only concerned with whether the sample mean is greater than or smaller than mu, we use the one-tailed function. The one-tailed probability levels are half those of the two-tailed, the x bar minus mu or mu minus x bar as numerators respectively. So we'll check that in just a moment. So here we see the percentage probability level for one-tailed would be 2.5, for two-tailed would be 5. So the two-tailed test would be at the 5%, and the one-tailed would be at the 2.5%. So here's where we see the critical t values for the degrees of freedom. So if you had an n of 5, your degrees of freedom would be 4. Your critical value would be 2.78 at the 5% for two-tailed, but that would only be 2.5% for the one-tailed. So it's more difficult to achieve statistical significance with the one-tailed than, it's easier to achieve the statistical significance at the one-tailed because 2.5% is less than 5% than it is with the two-tailed. So you get the same critical test statistic with a one-tailed, and you've already gone past, you're less than the 5%. So note that that these critical values depend on the quantity, the degrees of freedom, as noted up here. The point to be made here is that the 0.5 probability level is 0.5, percentage, which is would be basically p less than 0.005, as this is a percent. The 5% is p less than 0.05. So we don't usually use a p less than 0.005. We're usually using p less than 0.1, 0.01, and so on and so forth. So you convert these to decimals from percentage, and that's the probability level. Now let's begin to think of the t-test as applied to paired comparisons. So when we're performing a paired comparisons, the conditions for testing on the sample subjects, let me say, uh, must either be predominantly the same or are the same, and we'll get a better understanding of that in a moment. Basically what it means is if you use the same sample set and you test it with each variable, then you have a paired comparison. Each sample each sample subject is exposed to all of the variables, and you collect a data point under each variable condition. So in other words, if you had a patient population and you exposed them to placebo as well as the test drug, then you'd have a paired comparison. An unpaired comparison would be if you had two sets, a set of patients that only received placebo and a set of patients that only received the drug, then that's an unpaired comparison. So this becomes quite important in selecting your statistical test to know whether you've performed a paired comparison experiment or an unpaired experiment. So here let's take a look at an example in an experiment on the effect of electric current on the height of maize seedlings. 10 pairs of boxes of seedlings were put in various places and a weak electric current applied to one box of each pair. So this is a slight difference. Each of the boxes of seedlings are exposed to the same environment, and within that environment one is exposed to a different variable. So it's only the variable that differs, and this is a slight variation on the definition of the paired comparison that I gave you before, but obviously you can't grow seedlings with and then without the electric current and then be able to compare the effects at the seedlings that were at the same age. So there are some modifications to that simple format in determining paired versus unpaired as I described before. So pairing the boxes avoids errors likely to arise from putting the electric field boxes in different places from the unelectrified boxes, in which case any observed difference might be due to the different environments. So the average height of seedlings in each box was measured, and the average electrified minus the average unelectrified height in millimeters for each box pair was, as we see here, with the mean of 4.29 and a standard a variance of 1.04.1. So in this case, we wish to test the hypothesis that the electric current has no effect. The hypothesis is mu equals 0. So the t-test statistic is x bar minus mu, absolute value of that, over the standard deviation divided by the square root of n, so it would be 4.29 minus 0. We're testing if it's different from 0. Divided by the square root of 1.04 divided by the square root of 10 equals 1.33. This is appreciably less than the critical value of t at the 5% level, which with degrees of freedom of n minus 1 equals 9 is 2.26. Thus, there is no reason to reject the hypothesis that mu equals 0, and the results were considered to indicate that the electric current had no effect. So because our test calculated or observed test statistic was not greater than the critical value, we cannot reject the hypothesis, and therefore we say that the two samples are the same. The difference is not greater than 0 statistically. We don't often perform these types of tests, as you know. We're usually doing an unpaired comparison where we're just comparing the means between the two groups, and we'll take a look at that in a subsequent lecture, I believe. So note that in the paired comparison, the difference between each pair of readings constitutes the observation when the t-test is applied to test the hypothesis that mu equals 0. So the difference between the individual paired comparisons, this box against that box of seedlings, equal to 0? Is there really effectively no difference between the two? So this hypothesis is often called the null hypothesis. So do we reject the null hypothesis or accept the null hypothesis? So there is a difference between paired comparisons versus a correlation. With paired measurements, there is that difference when performing a correlation. So in paired measurements, the same variable is measured on the same subjects at different times or under different conditions. So this is more consistent with the definition that I gave, that you take measurements from every subject in the sample population under each variable condition, and then you make a paired comparison. What's the difference between this treatment and that treatment? And then you would get the mean for all those differences. However, in a correlation, you have two different separate variables that are measured on the same subjects at the same time under similar conditions. So you would separate the groups to do a correlation. So we rarely know the exact variances of two populations from which the samples are taken, so we need to know nothing about them other than what information is contained in the observations in each sample. So we end up estimating, of course, the sample variance by either of these two formula, for the two groups, and the means for the two groups. So now we want to test the difference between the means of any two samples where we have sample means, x bar and x bar prime. Obviously the formula is the sum of the observed data point values over the sample size. That's typical calculation for the means. And the variance, the same, the sum of the mean square differences over the degrees of freedom for each each sample S and S prime. And then the population variance can be estimated from that through these formula here, or another way of doing the formula by algebraic manipulation is shown here. Again, we note that we have sample 1 and sample 2, so we get the mean square differences, the sum of the mean square differences for sample 1 and then sample 2, the x prime, and divide that by the sample size for the first and then the second, the prime, and subtract 2, which is the same as n minus 1 plus n prime minus 2, the sum of the two degrees of freedoms for the two different populations. So the test when the population variances are equal using the t-test is shown here. The absolute value, so whenever we see absolute value, we know we're doing a two-tailed test. The difference between the two means, the means of the two sample groups, divided by the square root of the estimate of the population variance times 1 over the sample size 1 plus 1 over the sample size 2. With the degrees of freedom, basically the denominator used for the estimation of the population variance, sample size 1 minus 1 and sample size 2 minus 2, or in other words n plus n prime minus 2. So here we come to the critical values table to get the degrees of freedom and comparing the two groups. So if we had equal sample sizes of 5, it'd be 10 minus 2 would be 8. Is that on here? Well, let's pretend that it ended up being 6. And we're doing a two-tailed test, so to get 5% critical value is 2.26. And this is the test that we would be running if we are collecting two different samples, paired or unpaired, um, and well, mostly unpaired in this case, and we are comparing the means of the two samples. So this actually would be for an unpaired t-test. Now we want to test whether the observed variances of two samples differ significantly, and this is called the f-test. We'll talk about this more in other lectures, especially when we talk about the analysis of variance, but this can test whether you have significantly different variances when you're looking at two samples. So we test not the difference between the two observed variances, but actually their ratio. So that is if the variance for sample 1 and variance for sample 2 are the two sample variances, our test function is f critical test statistic equals s sub 1 squared over s sub 2 squared, where s sub 1 squared must always be the larger variance, so you always want a positive ratio, so hence the f is always larger than unity. So this is the approach for performing the f-test, to ask if the differences in the variances between the two samples is too large. So do they have the same, virtually the same variance, or statistically the same variance? So the critical values for f depend on the probability level, the degrees of freedom from your first sample with which the the variance, is calculated, and also if n1 is the size of the sample, then you have the degrees of freedom of n sub 1 minus 1. And on the degrees of freedom for your second sample, the smaller variance, s sub 2 squared, that is v sub 2, the degrees of freedom for your second sample equals the sample size for the second sample minus 1, where n sub 2 is the size of your second sample. So there is a significant difference at the 5% level, but not the 1% level, since the observed f is greater than the critical f at the former, but not the latter level. So in other words, if your observed f is only greater than the critical value on the table for the 5% and not the 1%, then you only have a significantly different variance at the p less than 0.05 rather than p less than 0.01. So we take it to the table here. Here's the 5% in the top and the 1% values. So we have the degrees of freedom for sample 1 and for sample 2. So if it was 6 again, we'd go with 6 here and come on over to 6. 1, 2, 3, 4, 5, 6. The critical value would be, I can't quite read that. I think it is 8.47. So let's go up to the 5% table, come down 1, 2, 3, 4, 5, 6, and it is 4.28. So it is easier to reach the critical test statistic value at the 5% significant level than at the 1%. No shocking surprise for us, right? Well, this